Hello everyone, welcome to another lecture on principles of computer security. In today's lesson, we are going to be looking at public key cryptography and RSA. In the previous lessons, we have discussed about different types of cryptography and we have briefly touched upon the differences between symmetric key cryptography and public key cryptography. So, in today's lesson, we are going to go into a bit more detail about that and understand how it can be used in computer security applications. So, the idea behind public key cryptography is, or rather, the underlying idea may be traced back to a significantly older times, even though the current application is significantly different. But the main idea there is there's some information that is made public to be known by everyone, and then there is some other information that is only made private, so that is only known to a select group of people. So, when it comes to public key cryptography, particularly when we compare that to private key cryptography, in private key cryptography, the main things that we discussed previously is that we have a single key. We have a single key, a single secret key. It can also call that the private key. And only that one key is being used for both encryption and decryption. That both the sender and the receiver, both of them are using the same key there. So, if that one key is compromised, the communication is compromised, or the security of the communication is compromised at that point. So, the protection lies on that one key. Because both parties have the same key and both of them perform the same functions of encryption and decryption using the same key, we would call this the symmetric key encryption. So, one of the other problems because of that is, because both parties can encrypt using the same key, if for example, one party takes a message and encrypts it with the key that they have and says that they received it from the other party, there's no way to determine whether it was not sent by the other party. So, this is again, we will come back to this a bit later when we discuss about public key cryptography and how it can solve these problems. So, these are the main sort of challenges that we already discussed in the previous lesson. So, we have also looked at some of the examples of these private key cryptography algorithms. So, this is something that we have already covered. In today's lesson, what we are going to talk about is the public key cryptography. So, here we don't have a single key, we have two keys, one of which is the public key and the other one is the private key. So, here what we have is each party in the communication. So, if you are communicating with another person, each party will have two keys. So, if you want to encrypt a message and send it to another party, you will have to encrypt it using their public key. Then they will decrypt it using the private key that they will have. So, the public key or rather the private key will be kept private. So that is the one that you will have to protect and keep it to yourself. And the public key, you can share it with anyone, because with public key you can only do decryptions. You will need the private key to do the encryptions. Because of this reason, we would identify this cryptography, this type of cryptography, as asymmetric. So that is, both parties in the equation, both parties of the communication are not equal, because they will have different sets of keys. So I will have my private key, then I will also have the public key that you sent me. And given public key is public, it can be shared with anyone. There's no problem in trying to protect them while it is being transmitted to the other party. There are a lot of theoretical backgrounds in terms of how these functions work. We will go into a bit more detail about those in a little while, but the main idea is that we will have two main keys there that we will use for encryption and decryption. So essentially what we will have is, say there is party A and party B. If these two entities want to send and receive messages in an encrypted manner, what they would have to have is, party A would have a public key and a private key. Similarly, B would have a public key and B would also have a private key. Of these keys, the private keys will be locked and kept with that particular entity. So the private key will be only available to them. But the public keys can be exchanged. So B will also have access to A's public key. A will also have B's public key. So now if they want to send a message, A will use B's public key and encrypt, and to decrypt that they will need B's private key. So encryption is using one key, decryption is using another key. So that is the very basic idea behind public key cryptography. One of the other things to remember is, just because public key cryptography has certain advantages doesn't mean it is replacing private key cryptography. There is still a lot of places where we would continue to use many of the private key cryptography algorithms. The ones that we have discussed previously in this course, we will continue to use them as part of many cryptographic applications. And public key cryptography will be a complementing factor, another way to do cryptography in certain application scenarios. When it comes to public key cryptography, it was designed or developed to address two main problems. One is called key distribution. So the problem with private key cryptography is, because both parties need to have the same private key to encrypt and decrypt, that key will have to be transmitted. That key will have to be distributed. So if I am A and B, we have the same key. So between A and B, we need to have a secure way of transmitting a key. Then transmitting a key, having a secure channel is the intention of using cryptography. And if we need a secure channel to send the key, then we need some other mechanisms to do that. So we need to have other key distribution methods to establish that. So that is one problem with public, or rather private key cryptography, that is being addressed with public key. Because in public key cryptography, key distribution is not a problem, because the only key that we need to transmit is the public key. Because if A needs to send something to B, A only needs the B's public key. Public key is what is needed for encryption. And public key, given it is not a private information, it can be sent even through an unsecure channel. So that is the advantage in terms of key distribution with public key cryptography. Then when it comes to digital signatures, another issue that public key cryptography solves, that is about making sure a message was not modified while it is in transmission. Say, for example, if we use private key cryptography, both senders will have the same key. So if one party modifies that, then it will not be practical to see that. Whereas here there are many ways we can do verification using public key cryptography mechanisms. We will discuss about digital signatures in much more detail in an upcoming lecture. Then one of the things to remember, particularly about public key cryptography, is they came to be in sort of as an invention. They became available in 1976 through two people that are pretty known in the cryptographic community, Diffie and Hellman. But one of the things to remember is, even before that, even before 1976, this form of public key cryptography has been made available for people in the classified community. So in the military and secret agencies type of environment, it was already known that such a cryptographic method can be used, but it became a public knowledge in 1976. So one thing to remember is public key cryptography is pretty old. It's not a new thing. It has been there for a while and it's very well established. So if we again think about public key cryptography, so here we have the use of two keys, one private key and one public key. Our public key is the one that we would use to encrypt messages and then also verify messages. The private key we would use to decrypt messages and sign messages. So here the thing to understand is, the encryption part and signature part will use the opposite keys. So if you want to encrypt something, you need public key, and if you want to sign something, you need the private key. Then if you want to decrypt something, you need private key, but if you want to verify the signature, you need the public key, or you can use the public key. So again, we will look at digital signatures in a bit more detail in a later lesson, but one of the main things here is people who need to encrypt messages, because people who need to send you something, they need to encrypt. They can just use the public key. Similarly, if they need to verify the signature, again they can use the public key. But with only access to public key, you cannot decrypt or sign. To sign or decrypt, you need the private key. So that is the main thing to remember about public key cryptography. To understand this public key cryptography in a bit more detail, let's take, for example, two padlock boxes. So we'll take the example of using padlock boxes. So the traditional message or the private key message is this. What we would do is we would put a message in a box, then we will lock it and send it. But the person who needs to unlock it will need the key as well. So they will need the key to unlock the box. They will need the same key to unlock the box. Whereas in public key cryptography, what would happen is, an alternative way of doing this is, you send the box, you send an open box to which you have the key. So you have the key for a box, you send that empty box open and send it to someone. And they, if they want to send you some information, they will put that information into that unlocked box, which is like the public key, and they will send it back to you, because they can, because it's an unlocked box, they can put a message and lock it, which is easy because there's no need to open it. It's just locking the message. So they can lock it and they will send it back to you, because as a receiver you can unlock it easily because you have the key. That is your private key. So that unlocked box is like the public key, and the actual lock to the box is the key. So the sender can send that without much difficulty. It is easy for them because they have an unlocked box, put the message and send. You as the receiver don't have a problem because you already have the key, so you can unlock it and see. And if we think about a third party, an attacker, for the attacker, they will have to pick the lock. So it can be assumed it is a hard thing because they don't have access to a key, so they will have to break the lock and get into that. So that is the basic idea behind public key cryptography. So what we would do in terms of an algorithm, for example, is anyone who wants to send messages to other people, we will have a lot of public keys. We can keep a lot of public keys. So this is Bob's public keys. And if Bob wants to send a message to Alice, for example, Bob will use the public key from Alice, which already is available. We'll use the plain text and the encryption algorithm with the public key and generate the ciphertext. So the ciphertext will be the encryption of the plain text using the recipient's public key. Then at the receiving end, Alice is going to receive a ciphertext that was originally encrypted using Alice's public key. To decrypt that, Alice would need the corresponding private key. So Alice would use the private key and the decryption algorithm to get the plain text from there. So here, this public key and this private key are a key pair. Both belonging to Alice, but the public key is made available to everyone so they can encrypt the messages and create the ciphertext. But the private key will only be available with the user to whom it belongs to, and they can use it to decrypt any of the ciphertext that were encrypted using their public key. So if we look at the main sort of differences between conventional encryption and public key encryption, or symmetric and asymmetric encryption, there are a number of differences that we can observe. That is, in symmetric, we will use the same algorithm for both encryption and decryption, whereas in public key we will use one for encryption and another one for decryption. Similarly, in terms of keys, in symmetric we will share the same key, and the algorithm, both the sender and the receiver, must have the same key and use the same algorithm to communicate. Whereas in the public key encryption, they must share their keys, but only their public keys. They will still have access to their private keys. They will not have to share that. So they will share one pair of keys, but other part of the key, they will keep it to themselves. So when it comes to security point of view, in symmetric, we should keep the key secret, because if we have the key, we can decrypt. In public key, only the private key must kept secret. So of the two keys, the private and public keys, only the private key must be kept secret, and that doesn't have to be sent to anyone, because it can always be private. Whereas the public key, which needs to be shared, can be shared, and it doesn't have to be protected. Then we would have the same requirements in terms of not being able to decrypt the message without having the key. So that requirement is there in both cases, because in both environments, if the private key is not known, if the secret key is not known, the decryption should not be possible. In the symmetric key environment, the one key is private. So if we don't have access to the key, but if we have some samples of ciphertext, it should be insufficient to determine the key. So we should not be able to guess the key using the sample of ciphertext and knowing the algorithm, because those are the things that will be known. So just by knowing those two things, we should not be able to determine the key. In the case of public key, the additional public key will also be made public. So whether we know the algorithm, whether we have access to the public keys, and whether we have access to ciphertext, even if we have those three, again we should not be able to guess the key. So rather the private key. So if we put everything into perspective, what we would have is, say we have A as the source of messages and B as the destination. So we have two parties. So now both of these parties, what they will do is A will use a key pair source. They will generate a key pair for them, a private key for A and a public key for A. Similarly, B will also create a pair of keys, public key for B and private key for B. So if a message needs to be sent, we'll first take this example, this box. So here what we are doing is, in this encryption box, we are using the public key from B and encrypting and sending something. If you want to decrypt it, we will use the private key from B. Another application that we will come to discuss a bit later, as I said, is about signing and signatures. That is where we would use the private keys and public keys in the reverse pattern to sign the messages, but we will come to that a bit later. So when it comes to public key applications, or where we would use public key encryptions or public key algorithms, there are many places it has advantages of being used. So essentially we can use it for encryption and decryption purposes, and there what we expect is secrecy of communication. So sender will encrypt, receiver will decrypt. They will use the two other pairs of public and private keys. So that is what we discussed so far. We can use digital signatures, that is for the purpose of authentication. So what we achieve with digital signatures is, one party is sending, the other party is receiving, but the sender will sign, so the receiver can make sure it is actually the sender who is sending. So say if we are sending something from, say, A to B, we all know A has a private key, and the expectation is only A has access to the private key, because this is the private key is a secret. So if A can sign the message, so the message is signed with A's private key, then we know only A could have done that. And at B, they can verify this using the public key. So that is the basic idea behind digital signatures, but we will look at that later. Then another thing that we would do with public key applications is what is known as key exchange. With key exchange, what we do is, for example, we can use the public key approach to share some information back and forth, and then establish a secret key for the particular communication, and then keep on using symmetric encryption approaches. Both parties are now using the same key. No two keys, no public key there, but the public key was mainly used for the key exchange part. So this is again another scenario that we can use public keys. So here what we try to achieve with key exchange is, we are trying to get private keys being used for the use of both parties, but use public key as a secure transmission mechanism to exchange these session keys. So there are a number of different algorithms that we can use for these as public key applications. There is RSA, which we will discuss today, and things like elliptic curve, Diffie-Hellman. We could discuss about this a bit later. And there are some differences. For example, Diffie-Hellman is not for encryption or digital signatures, but mainly for key exchange. Whereas DSS doesn't do key exchange, only for digital signatures. And RSA and elliptic curve, they support all of these. So there are different algorithms, different approaches for different purposes. We will look at some of these as part of this course. So now let's look at some of the main requirements that we will have to generate these two keys in a public key algorithm. So in a public key algorithm, we need these two keys. We need a public key and we need a private key. Let's see what are some of the requirements that we would have for such keys. So we would know the public key publicly. So everybody will know the public key. So there's no secrecy about the public key. So the public key is what we would know as the encryption key. So if we know that key and also we know the algorithm that is used, so one of the previous algorithms, if we know that algorithm, if we know these two information, can we find the decryption key? Is there any possibility of guessing the decryption key if we have access to the algorithm and the encryption key? So that is something that we want to avoid. So it should be computationally infeasible. So this is something that we don't want happening. We don't want somebody to be able to guess this. So we want it to be computationally infeasible. But from a computational point of view, we want it to be easy. We want it to be computationally easy to encrypt or decrypt the messages if key is known. If the key is known, then it is easy. If the key is not known, it is difficult, it is computationally infeasible, so they cannot break the encryption, so to speak. But if the key is known, then we can either encrypt or decrypt without much difficulty. So that part should be easier. And in some of the public key algorithms, either one of the keys can be used as encryption and decryption keys, but that is not always the case. So that is something that we'll have to discuss when we discuss specific algorithms. But at least the main two requirements we want to achieve with most of the public key algorithms. Then another thing that we would want in a public key algorithm is what is called a Trapdoor One Way Function. We want to have a Trapdoor One Way Function. So the basic idea of one way functions is, say if we have a one way function, so we can do this operation, say y is equal to fx, function of x, that this way of computation is easy. We can do this computation easy. But if you want to do the inverse of the computation, that must be difficult or infeasible. So That is the idea behind one-way functions. We can do one direction of conversion easily, but the opposite conversion should be difficult. Nobody should be able to do that. A trapdoor one-way function is, we would additionally have a key in this mix, and here if we know the key, we can easily do the conversion, and also if we know the key, we can also do the reverse. So if the key is known, both the operations are easy, both directions are easy. But if key is not known, then it should be infeasible. So in a public key situation, if the key is known, encryption should be easy. If the key is known, decryption should be easy. But if the key is not known, then decryption should be impossible. So the public key schemes that we would use in practice, they would rely on having such a trapdoor one-way function at their core. So essentially these are mathematical functions that we would use for this particular purpose. Another thing that we would try to do with public key schemes is, particularly for the sake of security, is if we have fairly smaller size keys, the key size is smaller, few bits, it would be easier to go through all the possibilities to do what is called a brute force exhaustive search. So to avoid having to use or having the possibility of being broken by brute force exhaustive search in a practical manner, we would use fairly large keys. If we use significantly large keys, then that would be safe. So what we would do is we would use large enough keys so that, but still making sure it is easy to decrypt and encrypt. So when we know the keys, it is easy to do those operations. But if we don't know the keys, it is hard to do cryptanalysis. So encryption and decryption is easy. Cryptanalysis, so that is trying to break the cryptography, is hard. So that is the point we would try to achieve with the size of keys. In many ways, we can see this as, these functions are theoretically, we can break these encryptions because these are computations. If we have enough computational power, it would be possible to break these. But what we want to achieve is impractical to break. So that is, with the level of computation that we would have, it should be impossible to break that. So that is what we would try to achieve there. But one of the differences that we would have, particularly with public key schemes and the symmetric key or the private key schemes, is that because this additional complexity is there, they can be sometimes a bit more slower than just using the public keys, private key schemes for encryption and decryption. Some of the functions may be slower, particularly on certain types of devices. Now let's look at one-way functions in a bit more detail, because these one-way functions are the sort of underlying building blocks for these public key algorithms. So the basic idea is, it is easy to compute but difficult to reverse. So one way of the computation is easy, the other way of the computation is difficult. Say, for example, let's think of a simple example of multiplying two prime numbers. So, if we take an example like this, say we take two prime numbers 3 and 5. If we multiply 3 and 5, we get 15. But if we were given 15 and if you were asked to guess what were the original two prime numbers, for smaller numbers it is fairly easy to guess. But if I give you a number something like 143, it would be a bit difficult, but a computer may be able to fairly easily do it. But if we go bigger and bigger, then we will come to a point where a computer will not be able to compute that in a suitable point of time. So that is what we would try to achieve with these one-way functions. So for example, with multiplying two prime numbers, the multiplication part is the easiest one there. So if we know the two numbers, multiplying is easy. But if we only know the final results, getting the origin two numbers would be difficult. For example, for 15 it is easy. For 143, maybe if we spend a bit of time, it may be when we go further and further, it would become more and more difficult, and at some point it would be impractical for the computers also. So one of the points about multiplying prime numbers is that it is still not, at least for until now, it is believed that it is a hard to factorize number. Finding the factors, finding which two multiplications will produce a number, it is a hard thing to do. Then the security of such a function will depend on if somebody can find that or not. So the suitable one-way function will have to be something like that. It is easy to compute the one-way part, the multiplication part is easy. Factorizing is difficult at a larger number scale, so that is okay. And then also we need to make sure that there is no efficient method to factorizing these numbers. But if somebody finds such a method at some point in time, then it would be a problem. So until that point, we can use that as a one-way function. Another one-way function that we would use is what is called modular exponentiation. So with exponentiation is basically raising numbers to a power. So raising a to the power of b, we would call it a to the power b. So that is basically exponentiation. So we have a multiplied b times. So this is something that you all pretty much know. Modular exponentiation is we do the exponentiation and then get the modulo for a particular number. So we would write this as a to the power b mod n. So calculating the modulo exponentiation is easy. So like multiplication, this part of the computation or this part of the calculation is easy. So if we know a and b, and if we know a, b and n, calculating that modular exponentiation is easy. But if we don't know B, but if we know the results, so that is, if we know the results for this calculation and we need to calculate B, then that would be a problem. That would be a difficult problem from a mathematical point of view. So that is what we mean by a hard one-way function. So one way of the calculation is easy, the other way of the calculation is difficult. So that is what we mean by a hard one-way function. Another one-way function is an example of a one-way function is modular square roots. So again, finding the square root of a significantly larger number, or finding the square root of something mod something. So if we have such a number, finding the square root of that could be a significantly complex task. So what we can essentially understand here is all of these are significantly complex mathematical functions. So the very basics of cryptography, very basics of public key cryptography relies on these complexities of one-way functions, where one way of the operation is easier to compute, the reverse of the operation or the inverse of the operation is difficult to compute. So we will use different sets of one-way functions in different public key algorithms to achieve that. So now let's look at a particular public key algorithm as an example. We will be looking at RSA. The RSA, the name comes from the three people who were behind RSA, Rivest, Shamir and Elderman. So this particular public key scheme came about in 1977, so a pretty old scheme, so to speak. And this is one of the very commonly used public key schemes. So the basic idea here in terms of the basic one-way function here is based on exponentation in the finite Galois field. So we may have briefly touched upon Galois fields, but the idea is it is both the operations would still fit within that same field of numbers. The basic idea is we would do modular exponentation in the finite Galois fields. So that is the basic idea of RSA, and we would use large integers, and the security is with the factoring of large numbers. So it's something as we previously looked at. So what we would have in a RSA encryption decryption scenario is we would have a public key and we would have a private key where n is the command prime, the encryption key and the decryption key are the main key parts. So n is the value that must be known by both parties. Then if you want to compute a ciphertext, we could compute the ciphertext where m should be in the range of between that selected n prime and 0, and then we would do the modulo n with e. So e is the key that we have. Then the reverse would be the D. We would use to get the message back, we would use another function, but now we would use the other key in that same modulo operation. So the sender would know the encryption key, the receiver would know the decryption key, and both of them would know the common prime n. So that is the basic idea of RSA encryption, and here the key to this system to work depends on the choice of modulus and exponents that we have to find. So we have to choose E and D and N. So these are the three things that we have to figure out, and by choosing these things in a suitable manner, we would be able to do this operation effectively. So as an example, if we have message is 88, then we would have to choose an n that is greater than 88. So let's say we choose 187. Then 88 to the power 7 modulo 187 is 11. Then 11 to the power 23 modulo 187 is 88. So here the magic part or the main interesting part is how we chose or how we came to this 23 and 7. Because 23 and 7 is the key pair. So 7 is the public key and the other key. So these are the two keys. So how did we find those two and 187? So the combination of finding these things is the interesting part about RSA encryption. We are not going to go into the underlying mathematics, the complex mathematics of RSA in this discussion, but because that is not key in this context of this course, but you can find out about those mathematical operations if you are keen. So when we think about the key generation for RSA, we have to determine the two prime numbers at random, but the problem is they should not be easily guessable by knowing the n. So we should find numbers in such a manner. So it should be sufficiently large so that people are not able to guess those numbers. So that is the main point behind this key generation algorithm or key generation. So if we look at the examples, or if we look at this from the examples of simple integers that we can see, it may seem fairly easy. You can guess these things, but we are talking about significantly larger numbers, like few hundred bits of numbers. So they are significantly larger. Hence, these computations and the inverse computations would be quite difficult. So that is what we would try to do with that. So when we think about the security of RSA, there are number of approaches are possible. There is one approach that is always possible in any cryptographic algorithm is brute force key search. We go through all the possible keys and trying to find that. But it would be infeasible in the case of RSA because of the larger size. Because given the large size of numbers, going for a brute force approach would be pretty impractical. Then there can be some mathematical attacks based on the mathematics if there are more efficient ways of computing, but currently it is a difficult factoring of modulus n is a difficult computation to do as of now. Then another attack is called timing attacks. So here we base the calculation based on how much time is taken for a decryption, and then what is known as chosen ciphertext attacks. So again, if we know some ciphertext and corresponding plaintext, then trying to guess the keys from that. So RSA can be immune to many of these for a number of reasons. So let's look at factoring problem, for example. With the factoring problem, what the idea here is, if we know the factor, so that is if we know n, can we compute or can we determine and compute the decryption key? So can we find the decryption key? So that is what we try to achieve. But the fact is, because we use significantly larger keys like 100,024, 2048-bit RSA keys, at that scale, it is impractical from a mathematical point of view to solve it from a factoring as a factoring solution. So that is the current situation with that. But with advancement of computing and in future these things could be broken, it may become possible with advanced computational applications, things like quantum computing and things like that. But that is not in the scope of today's discussion. But just remember, at least as of now, it is a secure algorithm. So the basic idea behind public key systems is we can use them in place of symmetric key systems, particularly for achieving a number of advantages. We can use it for encryption and decryption, which we can also do with symmetric keys. But in additionally, we can use this for digital signatures and also for key distribution. So because with public key cryptography in a public key system, we can establish a secure channel without having a secure channel. We can use public key system as the basis for exchanging secret keys, and then we can do symmetric key cryptography if that is more efficient way of computing. And to have a public key encryption algorithm, one of the main things that we would need is what is called a Trapdoor One Way Function. There are a number of examples of such one-way functions, but different algorithms may use different variations of such Trapdoor One Way functions. So they are essentially complex mathematical functions that are easy to compute in one way of the operation, but much more difficult to compute in the inverse of the same operation. And RSA public key encryption algorithm is one of the most widely used encryption algorithm, and it is still being used as one of the common encryption standards. So that's all for our discussion today in public key cryptography and cryptographic algorithms, public key cryptographic algorithms. We will look at some more examples of public key cryptography and some applications and so on in the upcoming weeks. We will also talk about digital signatures and so on as well in upcoming lessons. Until that time, if you have any questions, please do let me know through LMS or other usual communication methods. And if you have any concerns about things that we have covered so far, please let me know and we can go through them again if you need. And until next time, thank you for joining today. See you next time and bye.